Okay, in this video I'm going to continue on with my tutorials on thermodynamics and statistical mechanics. So I'm beginning also a subsection which I'm going to call Einstein Solids. And the first video in this particular subsection is called Two-State Systems. We're on video number 8 in total. So the previous video to this I discussed enthalpy, however that is irrelevant in this particular set of videos. What is relevant, however, is my video, or are my videos, on quantum statistics. And I'm going to assume that you've seen these videos, in particular where I discussed the rules for calculating multiplicities, and also where I discussed the multiplicity for bosons, because in fact we'll be seeing that we're discussing bosons at a later stage. So please look at my videos on quantum statistics. So what we're going to talk about now is two-state systems. So what is a two-state system? It's pretty clear. It's where a particle, each of the particles in your system can have one of two states. So think about a coin. Well, a coin can have a state of either head or tail, so it's two states. And if you ignore many of the other properties such as angular momentum and so on, you can think of electrons as also having two states, namely spin up and spin down. So two-state systems are proper physical systems that do occur, but they're also the simplest system to analyse, and that's where we're going to begin. So let's think of having three coins. So these are three two-state systems. How many different ways can we throw the three coins and get a different state? Well, the answer is as follows. The answer is that there are 8 ways of doing it, and there they are listed in front of you. So using the terminology of quantum systems, we can say that there are 8 microstates, where in each of these microstates we have designated what the state of each coin. So the sum of the number of microstates is equal to 8. That's the total number of states. For two-state systems, you should know, it's pretty straightforward as to why as well, that the number of microstates is equal to the number of possible, we'll say the number of states to the power of the number of particles. So if we had 100 coins, then it would be 2 to the 100 for the number of microstates in total. Now, is there any way to look at this to come up with macrostates? And the best way is to think about only the number of heads, or perhaps the total number of tails. But I'm going to do it with the total number of heads. So there are in actual fact 4 macrostates. Remember, a macrostate is the most ambiguous way you can fully describe the system. So if I say that there are anywhere between 0 and 3 heads, I have totally described my system. For example, 3 heads occurs here. 2 heads occurs here, and it also occurs here, for example. 0 heads occurs when there are 3 tails. So these are our macrostates. So using our previous terminology, we have S is equal to 1, the first macrostate, the second macrostate, the third macrostate, the fourth macrostate. And each of these macrostates has a certain number of microstates. The number of microstates for each macrostate is the multiplicity of the macrostate. So let's look at the multiplicities. The multiplicity of macrostate 1, which has 0 heads, is equal to 1. It only occurs once. In other words, there are 3 tails. The multiplicity of macrostate 2, which has 1 head, is equal to 3. The multiplicity of the third macrostate, which has 2 heads, is equal to 3. The multiplicity of macrostate 4, the final one, which has 3 heads, is also equal to 1. Now, what I'd just like you to note here, it's something similar to some sort of a Gaussian distribution, but so some of these are more probable than others. Clearly, the state which has the most multiplicity is the most probable state. So we can say that the probability of a state, we'll say n occurring, is the multiplicity of that state divided by the total multiplicity. And that's just some elementary statistics, something you should be very familiar with. Now, why is it that the total multiplicity is the sum rather than the multiple? So remember, we had 1, 3, 3, 1, and I said that there are 8 number of microstates. Whereas if you go, remember, looking at the quantum statistics videos, for example, we might have had, this is one for bosons. For one particular microstate you had the following: or one particular macro state, that was the multiplicity of the macro state. And then to get the multiplicity of the whole lot, we had to multiply across by all of the macro states. But it seems that for this particular two-state system, I'm adding them like this. Why am I adding, and why am I adding in this particular case and multiplying in others? And the answer is as follows. When we discussed the quantum systems, we broke total number of particles, capital N, equal in up. We broke it up like follows. So we put n sub 1 into macro state 1, n sub 2 into macro state s is equal to 2, and we broke down, let's say, we put n sub 3 particles into macro state 3. And each of these states, each of these macro states was independent. So the fact that we put n1 was independent of the fact that we put n2 someplace else. However, if you think about your coins, you either put all 3 coins into the macro state or you don't. You can't put 2 coins into one macro state, because then you don't have a full state. So the point is here is that the multiplicity for the macro state is equal to 1, because you put all 3 into that particular macro state. So you either put the coins in or you don't. So that's why you sum them. In other words, all the states are dependent, and that's why you sum rather than multiplying. So let's think about having 100 coins. If you have 100 coins, we know that the total multiplicity, so multiplicity all is equal to 2 to the 100. How many macro states are there? Well, there are 100 macro states. Namely 0 heads, 1 head, 2 head, the whole way up to 100 heads, leaving you 101 macro states. So we can see that by even multiplying, going from 3 coins to 100 coins has gotten an enormous number of microstates. We haven't really increased the number of macrostates. We haven't at all increased the number of macrostates proportionally. So let's look at the multiplicities of all these states. So the multiplicity of having 0 heads, so where s is equal to 1, the first macro state, and there are 0 heads. Well, that means there are all tails, and this can only happen once. Well, what about the second macro state where we have 1 head? Well, you could have head and a pile of tails. You have a tail, then a head, and then the rest are tails. You have 2 tails, a head, and then the rest are tails, or whatever. But think about it, you're just picking 1 particle. So there are only 100 ways to do that. There are only 100 ways to pick 1 particle out of 100 particles. So what about the multiplicity of the macro state number 3 where we pick 2 heads? Well, similar logic. This time we have 2 spots. Well, 100 can go into this spot, leaving 99, and then we have 99 choices over here. Now the important point which I discussed in my quantum statistics videos, let's say we have 2 particles A and B, and I choose A first then B, or B first then A. Well, this is the same state chosen 2 different ways. So this, as we'll see, n factorial way of counting is actually overcounting. So for every pair you must divide by 2, for every triplet you must divide by 3, or for every n particles you must divide by n. So what you're going to get here is divided by 2. So the multiplicity of macro state number 4, which is 3 heads, is going to be equal to 100 times 99 times 98. Divided by 3 for the triplets, divided by 2 for the pairs. And we can see, of course, where this is going, that we're going to get, I want this to become a factorial, and that means I have to divide by whatever is left in the sum. So let's say what we initially had was, we should get 100, 99, 98, the whole way down to 100 minus n plus 1. Okay, but we're missing all the terms down here to make the factorial, so just divide by those, and what we're going to get is, we're going to get n factorial divided by capital N minus n factorial, like that. Okay, so I did this quite quickly because, to be honest, I laboured it, I think, in the quantum statistics videos. So the whole point is that S is equal to S, the n heads is equal to capital N factorial divided by n minus n factorial. That's the multiplicity of a particular macrostate. Macrostate S, which has n heads, is capital N, which is the total number of coins, factorial divided by the difference between the number of coins and the number of heads, factorial. Alright, and as we said from the start, we have to do this kind of overcounting factor. We have to take into account that we've overcounted. So we had this extra factor of n factorial. So for two-state systems, this is the multiplicity for a two-state system having capital N particles. Alright, so that's all I've got to say about that. Thanks for watching. Please pass it on to your friends, subscribe to my channel, and if you're in a good mood, you might also click on an ad. Thank you.